Hi, this is Mr. Kutchell, and today we're going to talk about the kinetic theory of matter. Now, the kinetic theory of matter, oftentimes we abbreviate with the initials KMT for kinetic theory of matter. Basically, the kinetic theory of matter says that all matter is made up of small particles called atoms and molecules, and these molecules are in constant motion. And based upon this theory, we can describe different attributes to this particular theory, like temperature. We can describe temperature according to the kinetic molecular theory. We can also describe pressure according to the kinetic molecular theory. So we're going to go ahead and take a look at a PhET simulation real quick to take a look at how the kinetic molecular theory can describe temperature and pressure. Okay, so here's our simulation, and in our simulation we have a box right here. Here's the box, and within the box here we've also got a man that can open the box wider or close it. We've got a lid on it. We've got a temperature gauge. We've got a pressure gauge. We've got a way of pumping molecules into here. So the first thing we're going to do is we're simply going to add some molecules to the box. So I'm going to open this pump up, and I'm going to push it down, and in come some molecules. Notice they're moving kind of fast. They're bouncing around on the inside walls of the container. Now over here the pressure is no longer at zero. It was originally set at 0 atmospheres. Now atmospheres is a measure of pressure. So it's higher than 0 because the pressure is the simultaneous collision of all these molecules hitting the inside walls of the container. And if I were to add more molecules, the pressure would go up. So I'm going to add more molecules. There, I'm adding more molecules, the pressure went up. Okay? Now, I'm going to also add some heavier molecules. So I'm going to go ahead and add some heavier molecules. They're going to be blue. So I'm going to open this up, pump some heavy molecules in there. Now you'll notice as those molecules are moving around inside, the heavier molecules, the blue ones, are moving slower than the light ones, which are the red ones. Notice also that when I added more gas, the pressure increased. The pressure went up as I added more gas. Now let's change the box and increase the temperature. I'm going to add some heat. So I'm going to go ahead and add some heat. I'm going to increase the temperature. Oops, I'm going to go ahead and increase temperature by putting a flame underneath it. Notice what happened right up here. The temperature went up and the molecules are all moving faster. Now I'm going to remove some heat. I'm going to add some ice, cool it down. Watch the temperature drop. Watch the pressure drop. So as the temperature drops, the pressure is dropping. As the pressure is dropping, the temperature is dropping. Let's go back up. Add some more heat again. We'll do the opposite. If I add heat, what do you think is going to happen to the molecules? They should move faster. What do you think will happen to the temperature? It should go up. What should happen to the pressure? It should go up as well. And let's watch. So you add heat, the molecules move faster, temperature goes up, and the pressure goes up. Now, are all the molecules moving at the same speed? No. Some are moving faster, some are moving slower. We'll take a look at this in our next couple slides. So at this point in time, if you could go ahead and take out the video clip outlines found on your packet, we can go ahead and define some terms. So go ahead and put me on pause and find the video clip outlines in your packet. Okay, now that you've got your video clip outlines available, go ahead and put the definition in for the kinetic theory of matter. And the definition is that the particles which make up all matter are in constant motion. Go ahead and write that down. Okay, let's take a look at some other aspects of the kinetic theory of matter. First of all, as we saw in the PhET simulation, you'll notice that when the molecules were moving faster, the temperature gauge increased. In other words, the faster the molecules are moving, the hotter the temperature. Likewise, the slower the molecules are moving, the lower the temperature. Well, this all relates back to kinetic energy, because temperature and kinetic energy are closely related. So again, as we look at it, as a substance is heated up, its particles move faster. This value here, the velocity, is going to increase. Well, if this value, velocity, increases, so does the kinetic energy. So as a substance is heated up, the molecules move faster and the kinetic energy goes up. In a similar fashion, as the substance is cooled down, this velocity of the particles decreases. This value gets smaller, and therefore the kinetic energy goes down. So, the faster the molecules move, the higher the kinetic energy. The slower the molecules move, the lower the kinetic energy. So let's go ahead and take a look at how the kinetic molecular theory applies to the different states or phases of matter. We're primarily interested in the three main states of matter: solids, liquids, and gases. In our first example, I'm going to use ice to represent the solid phase. And in the solid phase, the particles, or the H2O molecules, are locked into a tight position, but they'll kind of jiggle or vibrate around. Now, in the liquid state, when water goes into the liquid state, the particles are able to move more freely. They're able to flow over each other, but they're not able to escape from each other. And so they're able to, again, move more freely, but have some attraction to each other. With gases, such as this steam from this geyser right here, when you have that steam, which is just water molecules coming out of that geyser, they're heated up so much that they're moving so fast that they're able to escape from each other. So if we take a look at this down here, this kind of represents what we've been talking about. We've got the solid with the particles locked into fixed positions that are kind of vibrating and moving around. Then we have liquids where the particles can move more freely over each other. And then we have gases in which the molecules can move very, very quickly around. To go from one to the other, to go from a solid to a liquid, you add energy in the form of heat. And then if you want to go from liquid to a gas, you add energy in the form of heat. Likewise, if you had a gas and you wanted to cool it down, it would eventually become a liquid. And if you cooled that liquid down, eventually it would become a solid. And this is how we can explain the different phases of matter as they relate to the kinetic theory of matter. Now, if you were thinking about these penguins as representing molecules, look at how they're all in one space. Which type of matter would they represent? A solid, liquid, or a gas? I would say they probably represent a solid. They're probably able to just kind of move around a little bit where they're at, but they can't move freely from one place to another. They kind of have to move in mass. They kind of move together. I don't know what's going on down here. We got a little huddle down here. I think they're playing football. That's what I'm thinking. Okay. So let's take a look at this simulation. In this simulation, what we're going to do is we're going to raise the temperature from room temperature. So you can see here we've got water. This is kind of looking through a microscope. And notice as we raise the temperature, what happens to the most molecules? They're going to start to go faster, aren't they? Look, they're moving faster. Temperature's gone up. Now we're going to cool them down more. And as we cool them down, they're going to start to move slower and slower and slower and slower. Okay? Now, they're not quite in their fixed positions. This is their fixed position representing ice. It's ice. The solids, these particles are actually vibrating just a little bit, but they're kind of locked rigidly in place. Okay, let's raise the temperature again and go to the other extreme. Let's go all the way up. And now you've got these molecules here, and some of them are able to leave. And since they're able to leave, you'll notice this the steam coming off, and the liquid level is going down. So that brings us to our next idea. And that idea is that temperature is a measure of the average kinetic energy of all the particles which make up a substance. Some particles are moving fast, some particles are moving slow, but we take the average kinetic energy. That's what temperature measures. Temperature is not a measure of heat. Temperature measures average kinetic energy. Now, when molecules move slower and slower and slower, eventually they can come to theoretically a stop. So when molecules come to a stop, we've reached a point that they call absolute zero. It's a theoretical point where all molecular motion stops, but it's not a point that's actually ever been reached. Notice it says a theoretical point. It's minus 273.15 degrees Celsius. Very, very cold. Okay? It's the coldest temperature that could theoretically occur. Now, scientists like this man right here, working in Massachusetts, have come within a trillionth, 1/1,000,000,000th of a degree, but they haven't quite gotten to absolute zero. That's really close, getting to 1/1,000,000,000th of a degree away from absolute zero. Well, that's about it for now. I'm going to try, like this penguin, to take off. We'll see you later. Bye-bye.